So let me now give you the definitions of the three trigonometric functions: cosine, sine, and tangent. To do so, we will first draw a triangle with one straight angle. So it has sides A, B, and C, and we call this angle over here x. And then what we know, or how we define these trigonometric functions is by telling us that the sine is equal to this side over that one. If the angle we are interested in sits here, so we get b over c. B over c. The cosine is equal to this side over c, and the tangent is equal to b over a. And since we know that in a fraction we can cancel out common factors, or we can multiply by common factors, we can do as follows, and we see that it is equal to the sine over the cosine. Now, what you probably know is that if you keep the three angles the same in a triangle and blow up one of the sides, then the other sides also blow up by the same factor, and so the sine, cosine, and tangent do not change, because these blow up factors all cancel out in numerator and denominator. So we might as well assume that c is equal to 1. Then we get that the sine of x is equal to the side b, and cosine is equal to side a. And now it's convenient to understand the number of properties of these trigonometric functions by drawing a circle of radius 1 and look at that one. So let me do it. Okay, we will draw the axis here. So we get a circle of radius 1. So 1 is sitting over here, minus 1 over here. I'm not quite sure it's completely correct. Well, doesn't matter. It's a little bit twisted. I will draw the circle to make and now you will be able to see how the graphs of cosine and sine look like by simply looking what happens to the cosine and so sine as x varies. Now, of course, connected with this point x, we have a point on the circle which has coordinates a and b. And what you see then is that if you look at this point AB, then since c is equal to 1, we have that the x-coordinate of that point is equal to cosine. So we have cosine of x sitting over here. The second coordinate b is in fact it's the sine because of that formula. So we have sine of x sitting here. Now, okay. We will draw a picture. So you can see that sine and cosine vary between the values minus 1 and 1, because as you move around the circle, you just get the first or the second coordinate of the point on the circle, and this can never exceed the values 1, can never be larger than 1 or smaller than minus 1. Now what happens if we look at the cosine function? So if x is equal to 0, then we get this point, we see that the first coordinate will be 1, so at 0 we are in 1. Then as you move along the circle, the x-coordinate decreases up to 0 at angle pi over 2, and then decreases further to minus 1 at angle pi. So pi over 2, pi, 3 pi over 2, 2 pi, and so on. We'll make it a little bit larger, this picture. And we get. So what happens is that cosine is 0 at pi over 2, then it decreases further to minus 1 at pi, and then it goes up again if you just move around the circle. And then it repeats itself. So there's a sort of repetition. After 2 pi, the values repeat themselves, and we call this the period. Period is 2 pi. So we have cosine x over here. Now, of course, the picture is not very nice. What happens to sine? Well, if we move x around the circle, then the sine is y. The y coordinate decreases to 1 at pi over 2, and then it starts to decrease to 0. So we start at 0. Let me take another color. It moves up to 1 at pi over 2, then it decreases up to till minus 1. You can see it. So if we move, the y coordinate decreases to minus 1 at 3 pi over 2, and then at 2 pi it's equal to 0 again, and then it repeats itself. So we get sine of x. And again, the period is 2 pi. Now suppose that we walk quicker, so we do not calculate cosine of x, but cosine of 2x. So instead of at x is equal to pi over 2, we are really already at pi. 2 times pi over 2 is pi. And if we put in the value x equals to pi, then at 2 pi, we are at 2 times pi, means we are already back. So we run 2 times quicker, and so the pattern starts to repeat itself quicker. So for cosine 2x we have period of pi. Now we'll derive some easy identities. And you can just see these from the circle. For instance, you can copy this triangle in various places. So here, we can copy it over here. We have an angle of x over here. We can just reflect it around the x-axis here. So we get this one. We have an angle of, well, in fact, minus x over here. And now we can infer many properties by just drawing these angles and triangles. So let us just look at one. Now what you see here in this picture is that if you look at the angle minus x and look at this point on the circle, and you see that the x-coordinate doesn't change, and the y-coordinate becomes minus this y-coordinate. So what you see is that if you look at the cosine of minus x, then it is the same as the cosine of x, but the sine, well, you see, you get a minus sign in front. And the same happens, of course, if, for instance, you look at this triangle. What angle, if we have x over here, then this is the angle pi minus x. And now if you now look at the cosine of that angle, well, you see that it is the corresponding point on the circle is this one. It has x coordinate sitting over here, so this is minus the x coordinate of this point. So the cosine of pi minus x is equal to minus cosine of x. And if you look at the sine, then we have the same y coordinate. of these 2 points have the same y-coordinate. And just by drawing this, you can infer many of these properties in a quite simple manner. Now we recall that we started with a triangle with one straight angle, so this means that the sum of the squares of these 2 sides is equal to the square of that side, and since these sides are cosine and sine, we get cosine squared plus sine squared is equal to 1. So this is a simple Pythagorean identity. Now we have some standard triangles, which you really should recall because they help you quite often in doing some simple calculations. We have 2 of them. One is, say, the triangle with 2 sides equal to 1. By the Pythagorean identity, this means that this side is square root of 1 squared plus 1 squared is square root of 2. Now, since the sum of the angles in the triangle is equal to 180 degrees, which means pi, this one is 90 degrees is pi over 2, so these ones are pi over 4. We can compute the cosine and sine in a quite easy manner, because now the sine of this angle is equal to this side over that one. Now we very rarely write 1 over square root of 2. We multiply numerator and denominator by square root of 2, and so we get 1/2 times square root of 2. And for the cosine we have the same relation. Now the other important triangle is this one, which has sides 2 over here, 1 over here, and if you make it into a triangle with equal sides 2, 2, 2, then you can see what the size of these angles are, because this one is, as in the previous one, pi over 2, the straight one. We have the sides of this triangle, the sum of the angles in this triangle is pi, and it has equal angles, so we divide it by 3, so we get pi over 3, so this angle is pi over 3. And this one is pi over 3, so half of it is pi over 6. And now you can compute this side, because we know that 1 squared plus square root of this one is equal to 2 squared is... I do something wrong. No, it's quite 4. Okay, yeah, so this is 4 is equal to 1 plus the square root of this one, so we have 3 is the square root of this length, so we get square root of 3 for the length of this side. So what do we get for the cosine of this angle? So this is equal to 1 over 2. If you look at this angle over here, then we just have computed the sine of that angle, so we get the sine is equal of pi over 6, and we get that the cosine of pi over 6 is equal to, so this angle, square root of 3 divided by 2 is equal to the sine of this angle. Now this you really have to remember. Yes, and one final remark over here as well. Of course we cannot divide by 0, so the tangent only exists for angles x for which the cosine is not equal to 0.